Water pollution. The release of substances into subsurface groundwater or into lakes, streams, rivers, estuaries, and oceans to the point where the substances interfere with beneficial use of the water or with the natural functioning of ecosystems. In addition to the release of substances, such as chemicals, trash, or microorganisms, water pollution may also include the release of energy, in the form of radioactivity or heat, into bodies of water. Types and sources of water pollutants. Water bodies can be polluted by a wide variety of substances, including pathogenic microorganisms, putrescible organic waste, fertilizers and plant nutrients, toxic chemicals, sediments, heat, petroleum, oil, and radioactive substances. Several types of water pollutants are considered below. For a discussion of the handling of sewage and other forms of waste produced by human activities, see waste disposal and solid waste management. Water pollution point source. Water pollutants come from either point sources or dispersed sources. A point source is a pipe or channel, such as those used for discharge from an industrial facility or a city sewerage system. A dispersed, or non-point, source is a very broad unconfined area from which a variety of pollutants enter the water body, such as the runoff from an agricultural area. Point sources of water pollution are easier to control than dispersed sources, because the contaminated water has been collected and conveyed to one single point where it can be treated. Pollution from dispersed sources is difficult to control, and, despite much progress in the building of modern sewage treatment plants, dispersed sources continue to cause a large fraction of water pollution problems. Domestic sewage. Sewage pollution. Domestic sewage is the primary source of pathogens, disease-causing microorganisms, and putrescible organic substances. Because pathogens are excreted in feces, all sewage from cities and towns is likely to contain pathogens of some type, potentially presenting a direct threat to public health. Putrescible organic matter presents a different sort of threat to water quality, as organics are decomposed naturally in the sewage by bacteria and other microorganisms. The dissolved oxygen content of the water is depleted. This endangers the quality of lakes and streams, where high levels of oxygen are required for fish and other aquatic organisms to survive. Sewage treatment processes reduce the levels of pathogens and organics in wastewater, but they do not eliminate them completely. Toxic Euglena bloom. Domestic sewage is also a major source of plant nutrients, mainly nitrates and phosphates. Excess nitrates and phosphates in water promote the growth of algae, sometimes causing unusually dense and rapid growths known as algal blooms. When the algae die, oxygen dissolved in the water declines because microorganisms use oxygen to digest algae during the process of decomposition. See also biochemical oxygen demand. Anaerobic organisms, organisms that do not require oxygen to live, then metabolize the organic wastes, releasing gases such as methane and hydrogen sulfide, which are harmful to the aerobic, oxygen-requiring forms of life. The process by which a lake changes from a clean, clear condition with a relatively low concentration of dissolved nutrients and a balanced aquatic community to a nutrient-rich, algae-filled state and thence to an oxygen-deficient, waste-filled condition is called eutrophication. Eutrophication is a naturally occurring, slow, and inevitable process. However, when it is accelerated by human activity and water pollution, a phenomenon called cultural eutrophication, it can lead to the premature aging and death of a body of water. Solid waste. The improper disposal of solid waste is a major source of water pollution. Solid waste includes garbage, rubbish, electronic waste, trash, and construction and demolition waste, all of which are generated by individual, residential, commercial, institutional, and industrial activities. The problem is especially acute in developing countries that may lack infrastructure to properly dispose of solid waste, or that may have inadequate resources or regulation to limit improper disposal. In some places, solid waste is intentionally dumped into bodies of water. Land pollution can also become water pollution if the trash or other debris is carried by animals, wind, or rainfall to bodies of water. Significant amounts of solid waste pollution in inland bodies of water can also eventually make their way to the ocean. Solid waste pollution is unsightly and damaging to the health of aquatic ecosystems and can harm wildlife directly. Many solid wastes, such as plastics and electronic waste, break down and leach harmful chemicals into the water, making them a source of toxic or hazardous waste. Waste is considered toxic if it is poisonous, radioactive, explosive, carcinogenic, causing cancer, mutagenic, causing damage to chromosomes, teratogenic, causing birth defects, or bioaccumulative, that is, increasing in concentration at the higher ends of food chains. Sources of toxic chemicals include improperly disposed wastewater from industrial plants and chemical process facilities, lead, mercury, chromium, as well as surface runoff containing pesticides used on agricultural areas and suburban lawns, chlordane, dieldrin, heptachlor. For a more detailed treatment of toxic chemicals, see poison and toxic waste. Sediment. Sediment, e.g., silt, resulting from soil erosion or construction activity, can be carried into water bodies by surface runoff. Suspended sediment interferes with the penetration of sunlight and upsets the ecological balance of a body of water. Also, it can disrupt the reproductive cycles of fish and other forms of life. And when it settles out of suspension, it can smother bottom-dwelling organisms. Thermal pollution. Heat is considered to be a water pollutant because it decreases the capacity of water to hold dissolved oxygen in solution, and it increases the rate of metabolism of fish. Valuable species of game fish, e.g., trout, cannot survive in water with very low levels of dissolved oxygen. A major source of heat is the practice of discharging cooling water from power plants into rivers. The discharged water may be as much as 15 degrees Celsius, 27 degrees Fahrenheit warmer than the naturally occurring water. The rise in water temperatures because of global warming can also be considered a form of thermal pollution. Petroleum, oil, pollution. Petroleum, oil, pollution occurs when oil from roads and parking lots is carried in surface runoff into water bodies. Accidental oil spills are also a source of oil pollution, as in the devastating spills from the tanker Exxon Valdez, which released more than 260,000 barrels in Alaska's Prince William Sound in 1989, and from the Deepwater Horizon oil rig, which released more than 4 million barrels of oil into the Gulf of Mexico in 2010. Oil slicks eventually moved toward shore, harming aquatic life and damaging recreation areas. Effects of water pollution on groundwater and oceans. Aquifer. Groundwater water contained in underground geologic formations called aquifers is a source of drinking water for many people. For example, about half the people in the United States depend on groundwater for their domestic water supply. Although groundwater may appear crystal clear, due to the natural filtration that occurs as it flows slowly through layers of soil, it may still be polluted by dissolved chemicals and by bacteria and viruses. Sources of chemical contaminants include poorly designed or poorly maintained subsurface sewage disposal systems, e.g., septic tanks, industrial wastes disposed of in improperly lined or unlined landfills or lagoons, leachates from unlined municipal refuse landfills, mining and petroleum production, and leaking underground storage tanks below gasoline service stations. In coastal areas, increasing withdrawal of groundwater, due to urbanization and industrialization, can cause saltwater intrusion. As the water table drops, seawater is drawn into wells. Discover how plastic debris is affecting marine life in the Pacific Ocean. See all videos for this article. Although estuaries and oceans contain vast volumes of water, their natural capacity to absorb pollutants is limited. Contamination from sewage outfall pipes, from dumping of sludge or other wastes, and from oil spills can harm marine life, especially microscopic phytoplankton that serve as food for larger aquatic organisms. Sometimes, unsightly and dangerous waste materials can be washed back to shore, littering beaches with hazardous debris. By 2010, an estimated 8 million and 7 million tons, between 3 million and 14 million tons, of plastic debris had been dumped into the oceans annually. And floating plastic waste had accumulated in Earth's 5 subtropical gyres that cover 40% of the world's oceans. See also plastic pollution. Understand global warming as a factor in the decline of dissolved oxygen in the ocean. See all videos for this article. Another ocean pollution problem is the seasonal formation of dead zones, hypoxic areas, where dissolved oxygen levels drop so low that most higher forms of aquatic life vanish, in certain coastal areas. The cause is nutrient enrichment from dispersed agricultural runoff and concomitant algal blooms. Dead zones occur worldwide, one of the largest of these, sometimes as large as 730 square km, 776 square miles, forms annually in the Gulf of Mexico, beginning at the Mississippi River Delta. Water quality standards. Although pure water is rarely found in nature, because of the strong tendency of water to dissolve other substances, the characterization of water quality, i.e., clean or polluted, is a function of the intended use of the water. For example, water that is clean enough for swimming and fishing may not be clean enough for drinking and cooking. Water quality standards, limits on the amount of impurities allowed in water intended for a particular use, provide a legal framework for the prevention of water pollution of all types. There are several types of water quality standards. Stream standards are those that classify streams, rivers, and lakes on the basis of their maximum beneficial use. They set allowable levels of specific substances or qualities, e.g., dissolved oxygen, turbidity, pH, allowed in those bodies of water, based on their given classification. Effluent, water outflow, standards set specific limits on the levels of contaminants, e.g., biochemical oxygen demand, suspended solids, nitrogen, allowed in the final discharges from wastewater treatment plants. Drinking water standards include limits on the levels of specific contaminants allowed in potable water delivered to homes for domestic use. In the United States, the Clean Water Act and its amendments regulate water quality and set minimum standards for waste discharges for each industry, as well as regulations for specific problems such as toxic chemicals and oil spills. In the European Union, water quality is governed by the Water Framework Directive, the Drinking Water Directive, and other laws. Great Pacific Garbage Patch, a zone in the Pacific Ocean between Hawaii and California that has a high concentration of plastic waste. The extent of the patch has been compared to the U.S. state of Texas or Alaska, or even to the country of Afghanistan. Garbage that reaches the ocean from the west coast of the United States and from the east coast of Japan is carried by currents including the California Current, the North Equatorial Current, the North Pacific Current, and the Kuroshio into the North Pacific subtropical gyre, the clockwise rotation of which draws in and traps solid matter such as plastics. Some 80% of the plastics in the garbage patch come from the land. It takes years for debris to travel from the coasts to the gyre. And, as it is carried along, photodegradation causes the plastics to break down into tiny, nearly invisible bits. While there are some larger objects that come from ships and offshore oil rigs, the garbage patch could more accurately be described as a soup of microplastics. The dimensions and depth of the patch are continuously changing. Scientists had been aware of the growing problem of plastic debris in the world's oceans since the late 1980s. However, the Great Pacific Garbage Patch came to public attention only after 1997, when yachtsman Charles Moore, returning home after participating in the biennial Trans-Pacific race, chose a route that took him through the North Pacific subtropical gyre. He found himself traversing a sea of plastics. When he returned to the area the following year, he discovered that the patch had grown in both extent and density. Moore began making speeches and writing articles, notably a 2003 essay in Natural History magazine, and he changed the mission of the Algalita Research Foundation, which he had founded in 1994 to improve water quality along California's coast. The organization now focuses on studying and publicizing the problem of plastics in oceans, in particular in the Great Pacific Garbage Patch. A 2006 series of articles in the Los Angeles Times about the garbage patch won a Pulitzer Prize and raised general awareness of the problem. In 2015 and 2016, the Dutch-based organization Ocean Cleanup found that the density of the debris in the garbage patch was much greater than expected and that the plastics absorbed pollutants, making them poisonous to marine life. The Great Pacific Garbage Patch is the best known of several such zones, others of which exist in the Atlantic and Indian Oceans. Light pollution, unwanted or excessive artificial light. Light noise pollution. Light pollution is a form of waste energy that can cause adverse effects and degrade environmental quality. Moreover, because light, transmitted as electromagnetic waves, is typically generated by electricity, which itself is usually generated by the combustion of fossil fuels, it can be said that there is a connection between light pollution and air pollution from fossil-fueled power plant emissions. Control of light pollution therefore will help to conserve fuel and money, and reduce air pollution as well as mitigate the more immediate problems caused by the excessive light. Although light pollution may not appear to be as harmful to public health and welfare as pollution of water resources or the atmosphere, it is an environmental quality issue of no small significance. Light pollution adversely affects professional and amateur astronomers, as well as casual observers of the night sky, because it severely reduces the visibility of stars and other celestial objects. The reduction in night sky visibility is a result of sky glow, upward directed light emanating from poorly designed or directed lamps and security floodlights. This wasted light is scattered and reflected by solid or liquid particles in the atmosphere and then returned to the eyes of people on the ground, obliterating their view of the night sky. The effect of sky glow from a town or city is not necessarily localized, it can be observed far from the main source. Light pollution is a problem not only for astronomers and people who simply want to enjoy the beauty of a starry night. Glare from road lamps, commercial security lights and signs, or even from a neighbor's bright and misdirected yard lighting can cause discomfort and distraction and adversely affect the quality of life of many people. Light pollution also has adverse impacts on birds and other animals. Many migratory birds, for example, fly by night, when light from the stars and moon helps them navigate. These birds are disoriented by the glare of artificial light as they fly over urban and suburban areas. It has been estimated by the American Bird Conservatory that more than 4 million migratory birds perish each year in the United States by colliding with brightly illuminated towers and buildings. Light pollution is considered to be one of the contributing factors in the dramatic decline of certain migratory songbird populations over the past several decades. Experiments have demonstrated that street lighting also reduces moth caterpillar abundance when compared with unlighted areas, and is linked to slowed caterpillar development. In addition, studies have shown these disruptions were more evident when street lights were outfitted with LEDs, light-emitting diodes, than yellow sodium vapor lamps. The quantity of light pollution from a given area depends on the number and brightness of light sources on the ground, the fraction of light that escapes above the horizontal, the reflectivity of surfaces near the light sources, e.g., roads, pavements, walls, windows, and the prevailing atmospheric conditions. Empirical formulas allow the calculation of sky glow levels as a function of population and distance from the observer. When sky glow levels are more than 10% above the natural background levels, significant sky degradation has begun. Even lights from a fairly small town with a population of only 3,000 people will cause significant night sky degradation for an observer as far as 10 kilometers, 6 miles, away. Light pollution can be reduced by using well-designed light fixtures with modern optical controls to direct the light downward, and also by using the minimum amount of wattage for the area to be illuminated. National and local government agencies can help by passing and enforcing appropriate light control laws and ordinances. Water pollution: slick oil spill, leakage of petroleum onto the surface of a large body of water. Oceanic oil spills became a major environmental problem in the 1960s, chiefly as a result of intensified petroleum exploration and production on continental shelves and the use of supertankers capable of transporting more than 500,000 metric tons of oil. Spectacular oil spills from wrecked or damaged supertankers are now rare because of stringent shipping and environmental regulations. Nevertheless, thousands of minor problems are reported each year, with the total quantity of oil released annually into the world's oceans exceeding 1 million metric tons. The unintentional or negligent release of used gasoline solvents and crankcase lubricants by industries and individuals greatly aggravates the overall environmental problem. Combined with natural seepage from the ocean floor, these sources add oil to the world's waterways at the rate of 3.5 million to 6 million metric tons a year. Oil spill damage. The costs of oil spills are considerable in both economic and ecological terms. Oil on ocean surfaces is harmful to many forms of aquatic life because it prevents sufficient amounts of sunlight from penetrating the surface, and it also reduces the level of dissolved oxygen. Crude oil ruins the insulating and waterproofing properties of feathers and fur, and thus oil-coated birds and marine mammals may die from hypothermia. Moreover, ingested oil can be toxic to affected animals, and damage to their habitat and reproductive rate may slow the long-term recovery of animal populations from the short-term damage caused by the spill itself. Damage to plant life can be considerable as well. Saltwater marshes and mangroves are two notable shore ecosystems that frequently suffer from oil spills. If beaches and populated shorelines are fouled, tourism and commerce may be severely affected, as may power plants and other utilities that either draw on or discharge into seawater at the shore. One of the industries most affected by oil spills is fishing. Major oil spills are frequently followed by the immediate suspension of commercial fishing, at the least to prevent damage to vessels and equipment, but also to prevent the catch and sale of fish or shellfish that may be contaminated. Deepwater Horizon oil rig. Fire. The immediate environmental effects of oil spills have been readily identified, but their long-term impact on the ecological system of an affected area is more difficult to assess. The cost of paying compensation to individuals and communities damaged by oil spills has been a major incentive to reduce the chances of such events taking place in the future. Oil spill cleanup. As yet, no thoroughly satisfactory method has been developed for cleaning up major oil spills. Though the spectacular spills of the last decades of the 20th century called forth great improvements in technology and in the management of coordinated responses. Essentially, responses to oil spills seek to contain the oil and remove enough of it so that economic activity can resume and the natural recovery processes of the marine environment can take over. Floating booms can be placed around the source of the spill or at entrances to channels and harbors to reduce the spreading of an oil slick over the sea surface. Skimming, a technique that, like the use of booms, is most effective in calm waters, involves various mechanisms that physically separate the oil from the water and place the oil into collection tanks. Another approach is to use various sorbents, e.g. straw, volcanic ash, and shavings of polyester-derived plastic, that absorb the oil from the water. Where appropriate, chemical surfactants and solvents may be spread over a slick in order to accelerate its natural dispersion into the sea. Onshore removal of oil that has penetrated sandy beaches and coated rocky shores is a laborious affair, frequently involving small armies of workers wielding hand tools or operating heavy construction-type equipment to scrape up contaminated debris and haul it away. Largest oil tanker spills in history. Two enormously important oil tanker spills that took place in European waters were the Torrey Canyon disaster off Cornwall, England. In 1967, 119,000 metric tons of crude oil were spilled, and the Amoco Cadiz disaster off Brittany, France. In 1978, 223,000 metric tons of crude oil and ship fuel were spilled. Both events led to lasting changes in the regulation of shipping and in the organization of responses to ecological emergencies such as oil spills. In North America, the Exxon Valdez oil spill of 1989 in Prince William Sound, Alaska, caused great ecological and economic damage, though it ranks well below the largest oil tanker spills in history if measured by the amount of oil spilled, 37,000 metric tons.